Hi everyone, I'm Liu Yan, a professor from Southeast University in China. I'm going to present IFCity, Intelligible Fair City Planning to measure, explain, and mitigate inequality. AI algorithms have been used everywhere. Concerns about algorithmic bias arise as AI benefits certain groups while disadvantaging others. Many visual tools have been proposed to examine fairness. However, they visualize tabular data with bar charts and scatter plots, mostly targeted for data scientist users or machine learning engineers. What about domains like urban planning that needs domain-specific visualizations, such as maps and 3D buildings, and requires domain experts and stakeholders to access fairness iteratively? We propose an interactive visualization tool called IFCity for urban planners to design fair neighborhoods. It balances the benefit from building locations across residents with different preferences. We got ideas from Lin and Day's intelligibility taxonomy, which explains things for non-data scientists, like answering questions like why not, what if, and how to for intelligent systems. Based on these questions, we identified design requirements, including provide a quantitative indicator of what inequality score, explain why the inequality was high or low by showing who were disadvantaged and where they live, and figure out why a certain location has high or low benefit. Simulate what might happen if the design changes and how to mitigate inequality. Design iteration timeline is also needed to compare between design iterations. Based on these design requirements, we introduce Intelligible Fair Allocation Framework in urban planning to perceive inequality, identify causes of inequality by attributing towards resident types or location by filtering problematic areas or viewing heat maps, and tracing the accessibility being too high or poor. Mitigate inequality by manually editing buildings, or following automatic fair planning recommendations, and review changes in inequality iteratively in a timeline. Let's see how we implement the IFAlloc framework. We extract building function types and their existing locations from map and building data, and identified different resident types and their preferences for different building functions from their trajectories. Suppose each resident has a home location. Let's break down how we calculate benefits for residents. Here is an example. For a residential building, we check the floor area of each building type within a certain distance to figure out accessibility. By multiplying this with resident preferences, we get what we call weighted accessibility. Now, the overall utility of living in the building is determined by finding the average weighted accessibility of all residents, and the difference from the initial utility defines the benefit. Users can view which resident types had unfair benefits or where the benefits were unfairly located. We use generalized entropy to measure how benefits are unevenly distributed. This metric is additive and can be decomposed into between group and within group inequality. So far, users are able to perceive inequality and identify causes. Let's see how to mitigate inequality. Users can directly edit buildings. Changes in the urban plan affect the location where each resident will live, thereby affecting the benefits and inequality. Here, we simulated population allocation with a well-known technique in which residents are more likely to be allocated to higher benefit locations. While the simulation helps to provide feedback on the user's design, it can be tedious for users to iterate designs on their own. To speed up, we provide a fair planning recommendation algorithm that optimizes fairness under a set of planning constraints. Let's see the basic visual design of IFCity. We developed IFCity as a web app with a 3D map. Users can examine the urban design by planning, zoning, and rotating the 3D map. Buildings with different colors represent different building function type. Users can track indicators to understand the various characteristics of the urban design, for example, planning area, population. Let's see how to edit and view buildings. You can add a new building, set its height, and its building type. New residents will be automatically allocated. Selecting on the building pops up its detailed information. You can also select a block to see its details. If city has specialized features to indicate and explain fairness in urban design, users can perceive fairness by inequality indicators. Benefit charts show group benefit mean, standard deviation, and global mean. Inequality index is decomposed into between group inequality and within group inequality per group. Colors on each block indicates its mean benefit. Users can identify sources of inequality by resident type or location. They can locate residents with high or low benefits, and view benefit distribution of each resident type. They can even trace accessibility and utility for residents in one building. We also provide a design timeline to track the changes of inequality and planning indicators. Users can compare between edited versions of designs. It is important to support users to understand how design changes can impact the fairness outcome. Once the design is changed, residents are reallocated, and indicators are recalculated. We also provide a fair redesign recommendation. You can firstly constrain benefit to be increased or decreased, and constrain how much total floor area can be changed. If city recommends which block to edit, and how much floor area of each building type to change, recommended blocks are highlighted on the map. Those blocks are also ranked by their contributions to inequality improvement. You can see the expected benefit and inequality. Now we present a synthetic case study of the neighborhood of Southern Boulevard in New York City. We can perceive inequality problems by looking at the indicator charts. We can see office workers, general consumers, and cultural consumers were relatively disadvantaged. Outdoor recreationists have much more benefits than others, and benefit varies a lot within each resident type. Between group inequality of outdoor recreationists and office workers are much higher than others. Within group inequality of most resident types are relatively small. To identify the cause of inequality, let's take office worker as the example. You can select office worker and highlight the buildings with high occupancy but low benefits. Alternatively, you can hide buildings and check blocks with high cylinders and red color. You can find the whole neighborhood is lacking of office supply. Adding office in the south may increase benefit of office workers a lot because most of them live there. To mitigate inequality, you can add office and commercial in the south. Check and compare inequality indicators in the timeline view. Keep editing until inequality index stops decreasing further. To further mitigate inequality, you can use redesign recommendation. Follow the recommendation one by one and edit buildings. You can see inequality drops a lot after few edits. Finally, we identified causes of inequality for 6 resident types. We evaluate the usefulness of each city with 3 urban planners and 3 urban designers. We find out that our intelligible features help them better identify causes of inequality. In mitigating inequality, our recommendation algorithm, if planned, achieves lower inequality score than human experts. Our domain experts stopped early with relatively high inequality score, while our algorithms could iterate more to achieve even lower inequality. To sum up, IFCity is an interactive visualization tool for urban planners to design fair neighborhoods by iteratively assessing and improving fairness. We proposed IF-alloc framework to perceive fairness, explain causes, and mitigate inequality. We demonstrate IFCity with a use case for redesigning a neighborhood in New York City. We find that the explanation features helped domain experts understand and improve fairness better.